So that's what goes here, this expression. And now, to understand the left-hand side, we need to take the differential of this expression. Because we always, when we go to the from the right-hand side to the left-hand side, we always take the differential. We already did it twice. We talked about the leftmost column where we took the differential of function. That was the easiest one. We did it here where we took the differential of this expression, like this, e dx plus q dy. It was slightly more complicated, but we got the right answer also. So let's see how we can possibly get the divergence. And this will finally demystify this last formula as well. So all we need to do is to apply the differential to this guy. Okay, let's do that. Apply the differential to this guy, following the same rule as before, nothing more, nothing less. What is the omega? It's going to be dA, dy dz, plus dB, dz dx, plus dc, dx dy. Okay, good. So what is dA? dA is the derivative with respect to x dx plus derivative with respect to y dy plus derivative with respect to z dz. And then I put brackets, and don't forget those guys, dy dz. Is that clear? That formula clear where it comes from? Okay? Ask me if it's not clear. This is our last lecture, so might as well. Well, not really last lecture, there'll be one more. Okay? But it's really simple. It's just take dA, that's dA, multiplied by dy and dz. So let's open the brackets and put this guys inside. We get this expression. Okay. So this is a good one. We have dx, dy, dz. They're all distinct. We'll keep this. But this one has twice dy. And we know that dy, dy is 0. There's nothing we can do about it. It is 0. It's a lost cause. Okay? It's gone. What about this one? Well, this is slightly more tricky. dz, dy, dz. But dz, dy, dz, first of all, we can switch dy and dz by using the rule, the antisymmetry rule. So this is the same. We put the negative side, dz, dz, dy. You see? You switch these two guys, so it comes out as dz, dy. And we put the minus sign. So it's the same. But now we've got dz next to dz. That's again 0. So this is 0 as well. So out of these three terms, only one survives, and that's dA dx times dx, dy, dz. Let's now look at the second one. In the second one, I will be taking derivatives of b with respect to x, y, and z. But each time I take derivative with respect to x, say, I spit out dx. Each time I take derivative with respect to y, I spit out dy. And same for z. But I already have dz dx, so I don't want to spit out any more dz's or dx's. So when I differentiate with respect to z or x, I will get 0. For the same reason for which this is 0 and this is 0. That means the only non-trivial term, the only non-zero term I get out of this guy is when I differentiate with respect to the variable which is not yet here. And there's only one such variable, y. Right? It's not a question, it's a statement. It's a variable y. I already explained why. So I just say cross, when I do respect to x is 0. With respect to y, I'm going to get dy, dz, dx. This is what I get from here when I differentiate with respect to y. I get this term times what I already had. That's how I get this. And the last one will also disappear, because again, there will be dz twice up here. And then we do the last one. For the last one, the first two terms will disappear. The only non-trivial term which I'll get will correspond to differentiating with respect to a variable that's not already there. Which variable is not already there? It's variable z. So you have to differentiate back to z. So you get dc, dz, dz, dx, dy. Okay, almost there. Let me summarize. Let me summarize. The answer has three terms. There is dA, dx, dx, dy, dz. There is dB, dy, dy, dz, dx. And there is dc, dz, dz, dx, dy. Okay? But now I have to follow my rules. And my rules tell me that dy, dz, dx. First of all, I can switch these two guys. I get a minus sign. And then I switch them again. I get two minus signs. But two minus signs is a plus. So I get back the expression dx, dy, dz without a sign, because I had to jump twice. If I jump just only once over dz, I get a minus sign. But if I jump twice, there's no price to pay. You see? So, well, you shouldn't generalize that last statement. It applies when you study fermions and the differential forms. So actually, this is the same as, I could just put dx in front, which would be the same expression as here. And likewise, for this expression, look, you got dz, dx, dy. You can jump, dz can jump over dx once, negative sign, and then over dy, second time, no sign. So again, you get back dc, dz with the usual product dx, dy, dz. So the end result is it is just dA, dx plus dB, dy plus dc, dz, dx, dy, dz. And that's the divergence of my vector field E, dv. This is dv, remember? Which is exactly what I get in this formula. Right? So if somebody asks you, why do you get a minus sign here, and you get a lot of minuses here, but in divergence theorem, we don't get any minus signs. Divergence is the sum. The respect to x, the respect to y, the respect to z, the sum. Now you can see, you can give a very clear answer, because when I calculate the derivative, the differential of that expression, I need to jump twice over those things. And when you jump twice, you get two minus signs. That's why there are no signs showing up. Whereas when you apply the differential, this guy, which is a one form, so it has like this, dx or dy, a single dx or a single dy, and not two dx's, or like dx dy or dy dz and so on. Then actually you have to switch them sometimes, switch once, and that's what gives you the sign. So you see now all these formulas, which look really bizarre if you just take them at face value and don't try to see an underlying pattern, they now start to make sense. These signs are there for a reason, and you can say in a way that the reason is that rule, that antisymmetry rule. That's where the signs come from, or don't, because sometimes you have to do it twice and then the sign disappears. Questions? Okay. Yes. That's right. So you're saying that we also have this formula for the cross product, that A cross B is equal to negative B cross A for the cross product. Right. Right. So the question is how exactly you get this out of this. Right. So the point is that when we're actually doing the integral, we also in the setup of the integral, we also use orientation. So in fact, it's not just the area, but it's oriented area in some sense. And oriented area is just the cross product. You see. So that's why when you switch, you get the same area, but with different orientation. Right? And that's the sign. The sign is not because the area is always positive, of course. The area is positive. But here we're talking not just about the area, but the area times the normal vector. And the normal vector can point one way or the opposite way. And that's determined by this right-hand rule or the corkscrew rule, whichever you like. Right? And so if you switch then the order, you get a negative sign. Very good. Very good. I'm very glad you asked me this. That's right. So there's one thing which I have not told you. Right? So I gave you 99% of the truth. I mean 95%. Right? And I'm glad that you asked me this. So that was exactly the question. Which orientation should I take on the right-hand side? So let's talk about orientations. In all of these formulas, orientation is very important. You can already see it here. We take f of b minus f of a and not f of a minus f of b. And that's because we use this orientation on the left-hand side. If we were using the opposite orientation, we would have to take f of a minus f of b to get the right formula, right? And then we talked a lot about orientation last time for Stokes' theorem, and also Green's theorem is just a special case of that. So in fact, to be absolutely precise here, I have to draw the picture that I have to choose orientations on both sides in a compatible way. Compatible way means that if I look at this orientation, then if I walk my head up on the boundary, the orientation should be such that as I walk with my head up with respect to this orientation on the surface should be to my left, which means in this particular case that it should go like this. This is the orientation. Only if I make compatible choice of orientations do I get this formula and not minus sign, not left-hand side equal to right-hand side up to a sign. But likewise, in this formula, I should also specify which orientation I choose. So let's talk about orientations in this formula. So here we have a left-hand side and a right-hand side. And on the left, everything is already oriented. You see, this is why this formula appears in the same row as those two formulas. We never talk about orientation here. We never talk about orientation here. That's because the regions, in this case, have the same dimension as the dimension of the ambient space. Here it's an interval on the line. Here it's a two-dimensional region on the plane. And here is a three-dimensional box in a three-dimensional space. These are what we call flat regions. They're not curved. Let's contrast this region to this two-dimensional region to this upper hemisphere. Upper hemisphere is curved. That is not curved. When you talk about the three-dimensional object, you may think that it is curved. But that's a misperception, misunderstanding. So the point is not the boundary of it could be curved. Just like the boundary of this one is curved. I'm not saying the boundary is not curved. The boundary is curved, fine. When I'm talking about the region itself, when I talk about the region itself, it means I take a point in the interior. I take a point in the interior, not on the boundary, and I observe that the small neighborhood of this point is just a piece of this plane. It's not curved in any way, right? Of course, on the boundary, that's not the case. I'm talking about the interior. I'm talking about this two-dimensional region, not about the boundary. Likewise, if I take a point in this box, the small neighborhood of this point is flat. In fact, we cannot really imagine a curved three-dimensional object. It would be very difficult. You see? Because a curved three-dimensional object would have to live in a four-dimensional space, just like a curved two-dimensional object would have to live in a three-dimensional space. Okay? So since we are not going to the four-dimensional space, all our three-dimensional objects are flat. And for a flat object, there's a canonical orientation. That's the coordinate system x, y, z. We know which coordinate is first, which coordinate is second, which coordinate is third. And that's the orientation. Or more precisely, we have to fix the cyclic order of the coordinates. So the left-hand side does not require any additional information. That's just our familiar triple integral. When we talk about triple integrals, we do not talk about orientation because there is no need to talk about orientation. They are well defined. Once we choose the orientation of the three-dimensional space. But the double integral on the right-hand side requires orientation because that's a surface integral. And surface integral depends on the choice of the orientation of the normal vector. In this particular case, for example, giving it orientation, giving the boundary orientation would mean on each of the sides to say the vector sticks out or goes inside. Likewise on the bottom goes down or goes inside. Likewise at the top goes. So there are two choices. Either they all stick out, they all go outward, or they all go inside or inward. Okay? So for a region which is a boundary of a three-dimensional domain, there are two possible orientations, inward and outward. And we have to say which one we should use here so as to have this equality and not this equal to negative that. I mean, there are two choices. It could be this or it could be negative that. And the correct statement of the divergence theorem is that you have to take this with outward orientation. Outward orientation. So now everything is correct. Now it's 100%. I give you 100% of the truth. And we have a little time to do a couple of examples. So how can we use divergence theorem? We'll talk some more about this general pattern on Tuesday. But now I just want to give you a couple of examples just to illustrate applications of this formula. How can we use divergence theorem? Well, basically in the same way in which we use those formulas. Sometimes it's much easier to calculate the left-hand side than the right-hand side, or the other way around. Usually it's this way, not the other way. So for example, suppose you have a vector field which is x cubed I plus y cubed j plus z cubed k, and B is a unit ball. Well, let's just say M is a unit sphere. And so you're asked to calculate the double integral of E dot ds over M. Okay, so it's not impossible to do. You have to parameterize the sphere by using spherical coordinates, and then you'll get some formula. But it's rather complicated. So actually, in this case, it is worthwhile to apply this theorem. In fact, the best example to illustrate this would be I could choose a vector field E for which divergence is equal to 0. If the divergence of a vector field is equal to 0, it could be some really bizarre vector field, but its divergence would be 0. In other words, I could take a vector field. So this is a digression. I could take a vector field where here I would have some function, e to the tangent of z cosine y I plus sine of cosine. Just imagine the most bizarre function you can concept. I guess my imagination is not that It's not that wild, but I'm just trying to emphasize, I'm just trying to give you some weird functions. But you have to be careful. You have to make sure that the divergence is 0. Something like this. And suppose you get a problem like this. So nobody in the right mind will give you such a vector field unless there was some drastic simplification that could happen, right? So in this particular case, the simplification is obvious. If you take the divergence takes the derivative of the first guy with respect to x, and you notice that this does not depend on x at all. So this will be 0. The derivative of this with respect to x is 0. The derivative of this with respect to y is 0. The derivative of this with respect to z is 0. So divergence is 0. So usually, if you look at the homework, you might see some really bizarre vector fields. Apply divergence theorem. You will not regret it. Okay? You might actually get 0. And then that's the end of the calculation, right? Because if it's 0, that means this integral is equal to this is equal to 0. What I'm giving you is not quite as obvious, not quite as obvious a gimmick, but it's a more realistic situation where the divergence is not 0. But it's very close. It's very simple because, so what do I get in this case? In this case, the divergence of E is 3x squared, right? That's what I get by differentiating this, plus 3y squared, that's what I get by differentiating this with respect to y, plus 3z squared. So it's actually 3 times x squared plus y squared plus z squared. And that means that my integral, my surface integral, can be written as an integral over the interior of the sphere, over the unit ball. So it's a triple integral of the function, which is 3x squared plus y squared plus z squared. But of course here I pass to the spherical coordinates. So this is actually 3 rho squared. And I end up with the following thing. I get 3 rho squared. Then I have to remember the Jacobian, rho squared sine phi. And then I have d rho, d phi, d theta, which is very easy to compute. Right? So that's a good illustration of how you could apply divergence theorem. We will talk about, I will give you more examples and talk more about how to give you tips for the exam problems on Tuesday. And remember, the lecture may not be televised, so you want to be here on Tuesday. I want to see you all on Tuesday, okay? Yeah. And thank you for being such a great audience. It's been a lot of fun.